Okay, well, this is the beginning of the graphene program. This is turning trash into cash in a flash. This is tough tech. It's something different than we've been hearing in this conference. This conference has been all about software, but that software has to reside upon something, has to have some material upon which to reside. I've spoken before in this conference, but this method that we're talking about today is flash fuel heating. It sits in this regime. We've done other work with laser-induced graphene, and that's formed in microseconds. CVD or hydrothermal methods usually take minutes to hours. This forms in milliseconds to a second, somewhere in that region. So it's very fast formation. And the way this works, and everything I described to you today, will work this way. It's really a very simple idea. You put in this case, any carbon material between two electrodes. You apply a high voltage and a high current. It is not a plasma. We are putting current through the system, and you pump in enough energy that all the carbon-carbon bonds break in whatever material that you have put in. And that's not hard to do. You break all the bonds, and then they reassemble. And they reassemble as the thermodynamically most stable system, which in this case is graphene. And so you can see here that within 3 milliseconds, the temperature reaches over 3,000 Kelvin. Now, 3,000 Kelvin is very close to 3,000 centigrade when you're up at thousands of degrees. It's very little difference. And it heats at 10 to the 4th to 10 to the 5th degrees C per second, which means that nearly 100,000 degrees per second the temperature rises, and it cools at 10 to the 3rd to 10 to the 4th per second, and you can easily hit 4,000 degrees if you like. And this is the way it works. all the heteroatoms will sublime out at that temperature, and so you come out with a very clean form. This was invented in my group by Dewey Long. He was a graduate student at the time, and there's a big burst of light, so we call it flash graphene. Graphene is non-toxic, and it's even used in several medical applications. It's naturally occurring in the environment. So graphite will shear off graphene in riverbeds. And if you've ever had a drink of whiskey, that comes out of a charred barrel. Many years ago, we looked at whiskey under a microscope, a transmission electron microscope, and we found graphene. So people have been drinking graphene for a long time. And its natural agglomerates are the natural mineral graphite. So it's the natural mineral graphite. And so we don't have to worry about it as much. It's a terminal natural sink. Anything that you bring up from under the ground, any carbon asset, whether it's natural gas or coal or oil, that's going to end up in the CO2 cycle eventually. Even if you just turn it into just carbon, you throw it out, plants will take that up. The plants will die, it'll enter the CO2 cycle, but not graphene. Graphene is very slow in microbial decomposition, and this is why we have graphite mines in the world. If microbes could eat graphite, we would have no graphite mines in the world. So this is a great place to store carbon. You only have to store it for 100 years, because in 100 years we'll have different energy sources anyway. It's good in composites of all types. There's no water in the process. There's no solvents. There's no purification. It's self-purifying. At these temperatures, silicon sublimes out about 2,800 Kelvin. Aluminum around the same temperature. Carbon doesn't sublime out until about 3,900 or 4,000 Kelvin. You say it must be a lot of energy. It's actually $30 per metric ton to make graphene. So you take coal, which is a high carbon compound, and you flash it, you put in $30 worth of electricity, and you say, how can that be? You just said you put a high voltage and a high current. Well, the current only is going for fractions of a second. So it's a lot of energy, but very quick. The current price of graphene is about $50,000 per ton, so there's a lot of room to capture, to bring back in the markets. We've started this company, which I mentioned a few years ago, and I know the CEO was here last year, John Van Leeuwen, Universal Matter. They have built their 1 ton per day facility, so we're producing 1 ton per day in this pilot facility. But what they've learned is if they just sell the graphene, people just try it and it doesn't work, because you can't just throw this in and expect it to work in your favorite formulation. It's not pixie dust. And so they've worked a lot to build formulas. So these are formulations for cement and concrete. You add a liter of material to a cubic meter of concrete. Asphalt is a complete replacement for the butadiene styrene rubber in asphalt. It raises the working temperature of the asphalt 11 degrees centigrade without affecting the lower temperature. It's going to paint, coatings, and rubber tires. Well, how is this an environmental effort? Well, 30 to 40% of all food worldwide is thrown out. And you have to throw it out because it goes bad. How many of us have cleaned out a refrigerator? It just goes bad. and that forms not just CO2 in landfills, that forms also methane in landfills. Plastic, big problem in the world. Rubber tires, big problem. Doesn't matter. Any carbon source, you flash it, it'll turn into graphene. Here's all the different recyclable plastics. Doesn't have to be recyclable. We can run on engineering plastics, which are not recyclable. The problem with recycling is this. It makes us feel good, but the price of virgin plastic and the price of recycled plastic is the same. And the recycled plastic can't be used in food, can't be used in pharmaceuticals, and has inferior properties. Human beings stand there and separate all the different 7 types of plastic. That's the expensive part. Here, you can have them all mixed together. It doesn't matter because you bring them all back to carbon bonds, and then they reassemble. We had a collaboration with Ford. Every car in Europe comes back to the manufacturer after the lifetime of the vehicle. So that means after 30 years or 40 years, the car comes back to Ford, and they're only allowed to landfill 5% of the car. Well, the metals are recyclable. What do you do with the plastics where you have 250 kilograms of plastic in the vehicle? Every wire is stripped, every seat cushion, everything. We got 10 pounds of that. We flashed it, we turned it into graphene. We sent it to Ford Detroit. They put it in their composites because every Ford has had graphene in it since February of 2020. It's in the underhood insulation, it's in the foam cushion seats, and it lightweights the vehicle. And so you can see the composite foam cushion, and they said it does everything it's supposed to do. It absorbs the sound, it gives the stiffness that you like, the compression forces that you like. I said, send me the composites. So they sent the composites. What do you think we did with the composites? We flashed them. We turned them into graphene. And so you see the life cycle here. You just keep turning it into graphene and turn it right on around. Coming out at the same time, last year I sent my student here and he talked about this, that what happens to all the hydrogen atoms that are in that plastic? Well, they form H2. H2 is preferred over methane, ethane, and propane, which are down here, because the hydrogen bond is about 22 kilojoules per mole stronger than the carbon-hydrogen bond. And you say, well, how much does it cost you to produce the hydrogen? Well, if you sell the graphene, not at its current price, but at 1/20th of its current price, at $3,000 per ton, which is about the same price as a plastic, you would be making hydrogen for minus $4.30 per kilogram. Minus, because you're making so much on the graphene side. So it's a free way to make hydrogen fuel. How about the rest of the periodic table? We just talked about carbon. We've extended this to the rest of the periodic table. So we've made 22 other materials here. These materials, some of these materials cost $600 for a tiny little piece, and we can make these in gram quantities. This will be fully scalable, so we can extend the same process to other materials in the periodic table. How's this in environmental and waste management applications? Well, you may have heard of PFAS. PFAS is per- and polyfluorinated alkyl substances. It's in all our water. It's ubiquitous in our society. It's in all of our bloodstreams. And you can take this material and it's in water. Well, how do you get it out of water? Because they've just passed new standards. So every municipality is going to have to start doing this, running their water through activated carbon to get out the PFAS. These are these fluorinated compounds. Well, what do you do with it once you've got it like this? Well, we just put it in the flashing unit. We add some calcium hydroxide. We flash it, we get graphene. And the fluorine ends up on the calcium, forming calcium fluoride, which is the natural mineralized form of fluorine in the environment. And when you do that, you say, well, how much does this process cost you? It costs negative $1,900 per ton. How can it be negative? Because you can sell the graphene, and you get this material, you get the graphene, you get the calcium fluoride. So it's a way of cleaning things up at very low cost or negative cost. What happens to all those wind turbines and old aircraft at the end of their lifetime? They are buried whole. Or here's the wings from these wind turbines. Why do you do this? You've seen these. These are very large structures. What do you do with these? They're very hard to deal with. They're carbon fiber mixed with plastic, or they're plastic and glass fiber. We flash it. We flash it, you get silicon carbide. So you get silicon carbide in this process, and it's about $100 per ton to make silicon carbide. And if you add iron, you'll get one-dimensional structures. You put that in concrete, you put that in cement, you get a 70% increase in the flexural strength and a 57% increase in the modulus of elasticity. Well, what about higher value applications? I have a battery company, and you can put these in batteries. You can use these as battery anodes, and they work exceedingly well as battery anodes. So the silicon carbide quality is very high because this got very hot, and the non-silicon and carbon elements have sublimed out. We're flashing the ground. If there's contaminants in the ground, whether it be toxic organics, heavy metals, or PFAS, we can put in electrodes, flash the ground, and our process is much less expensive than other processes. We've extended this to battery recycling, both the anode, the cathode, or the mixture, the black mass. So we can flash all of these and purify this and get the elements back out of them, because metals are theoretically infinitely recyclable. It's not like a plastic that you want to keep this structure together. You're just going right back to the bare metals, and we flash them, and our price is much cheaper. And then we've developed a new process for this. We flash it under an atmosphere of chlorine gas. You say, well, what does that do? Well, what we do is we're taking advantage of the free energy of formation of the metal chloride. Why would we want the metal chloride? Look at this. Iron oxide boils at 3,400 degrees centigrade. Iron metal boils at 2,800 degrees. Iron chloride boils at 315. We can dramatically lower the boiling point by thousands of degrees by converting it to the chloride. Titanium oxide boils at 3,000. Titanium metal boils at 3,200. Titanium tetrachloride boils at 136. So we have three knobs to turn now. One is the heat of formation of the chloride. That's thermodynamics. The other is the activation energy of the chloride formation. That's kinetics. And the third is the boiling point. And with that, we can do these separations. There is a material called sputamine. Sputamine, there's many reserves of sputamine all around the United States. Only 1/3 of lithium is mined from sputamine because it's more difficult than getting it from brines. Here's the route that you have to go through, all of this route, this roasting, this leaching. You have to control the pH. You have to add acid. You have to add base. And this is the typical sulfation method. What we do is we just take the raw ore, we grind it up, and we flash it. It has about 5%, 6% lithium by weight, much more than in the brines. The brines in the United States are about 0.25%. You flash it. Here's the thermodynamics. Watch this. So aluminum, anytime you're below this dotted line, when the free energy is less than zero, that is a spontaneous reaction at that temperature. So lithium will react with chlorine at about 500 degrees to form lithium chloride. The aluminum and the silicon that are in the sputamine do not react until well over 2,000 degrees. And then lithium chloride boils at 1525. And so what we'll do is we'll just flash it at 1525, and boom, lithium comes out. You just grind it up, flash, lithium comes out. No more adding chemicals, no more adding things, and out comes the lithium chloride. We got 93% yield, 92%, 93% purity, 92% yield in 30 seconds. No water, no solvents. This is what we're doing. This is the ability now to take this flash chemistry and extend it to the rest of the periodic table. This is red mud. Red mud is a toxic byproduct that comes from aluminum mining. There's contamination all over the world from red mud. It's red because there's iron oxide in there, hematite, and that's what makes it red. Here's what you have to do to pull the iron out so that you can get out of the aluminum. All of these steps have to be done. We just take it, we can do it flash Joule heating under chlorine at 1450 in 30 seconds. Iron is removed and all of these other elements are removed, and that aluminum that's left can go right on into the process after that. So what have we done? We've done lithium from spodumene. We've done gallium from light-emitting diode waste. We've done indium from indium tin oxide, transparent electrodes, and there's gold in there as well we get out. Tantalum from tantalum capacitors. Iron and rare earth elements from the red mud or bauxite residue. Cobalt from hardened tools, have cobalt in them. We just flash the hardened tools, and out comes the cobalt. Heavy metal removal and rare earth elements from coal fly ash. That's what's left over after burning coal. Rare earth element magnets. We just flash them, we get the rare earth elements back out. The precious metals and rare earth elements from printed circuit boards. You have mountains of printed circuit boards from these server farms. Every time you store something to the cloud, mountains of printed circuit boards that are recycled, that are changed over every 3 years. What do you do with those? Toxic waste. We just grind them up, flash them, we get the elements back out. And remember, we're not just pulling them all out at once. With the chlorination process, we were pulling one out, and then the next, and the next, and the next, separating them. Lithium, cobalt, manganese, nickel, and graphite from battery waste. So we've published all of this recently on the flash separation of metals by flashing under chlorine atmosphere. And so last night I was asked what are the different companies I've started, and I couldn't remember them all, so here they are. But what's interesting here is you're going to hear today from first you're going to hear from Walt talking about single layer graphene, and then Michael is going to present, and he's the CEO of MTM Critical Metals. So this company has been taken public through a reverse merger. So we started this company in the US and then we reverse merger. It's been taken public. It's on the Australian Stock Exchange, so you can invest very easily. And they've gotten all the metals, so all of the metal flashing they get. Universal Matter is the company that does these 2D materials, does graphene, and they're at a ton a day. That's still a private company. And then we have other companies around this. But with that, I'm going to just turn it over to to Walt to go on and show you about single layer graphene.
Okay, well, I want to thank George for inviting me to come here. It's the first time I'm at this conference, not the first time in Seattle. But in any case, I'm going to talk about a totally different kind of a graphene. This is epitaxial graphene. These are monolayer graphenes on silicon carbide, something that I've been working on for the last 20 years. And in fact, this is exactly the 20th anniversary of this whole program. So it's been around for a long time. And that was interesting. It's been a long ride. And I'm not going to be talking about tons of graphene. I did a quick calculation. I think I used 100 micrograms over my whole life. So that's what it is. You can figure out how much 100 micrograms is. So let me see if I can manage this clicker. So there were two major papers that came out in 2004 in October, basically. And one was the paper that I was working on, the so-called epitaxial graphene in 2004, and the other one came from Manchester, and that was also on graphene, and two entirely different approaches to it, whereas we were working with a graphene on silicon carbide called epitaxial graphene. On the other side of the pond, they were working on exfoliated graphene that they made simply by taking graphite and a Scotch tape and peeling it off. And there are other differences. Well, we were explicitly working on trying to make a new electronic material, and we were actually working on decades of prior work. But on the other side, they actually didn't realize that graphene had been around for a very long time already, and I won't get into that. But for some reason that I do understand very well, the physics that was involved in working with this so-called Scotch tape or exfoliated graphene, that actually is not even graphene. It was multi-layer graphene, actually technically that's thin graphite. And you will see that the confusion between thin graphite and graphene is quite substantial. And many people make it equivalent. And I want to kind of work on that a little bit because they're not the same thing. But we were really into looking at the special properties of monolayer graphite and how you can make electronics out of it. That's the point. Fine. Well, let me go the other way. Now I'm getting confused about my... It's a bit there. So I want to give you some graphene basics and some things you might know or might not know. Well, graphene is a single layer of carbon, and hexagonal for carbon, and it's actually basically what graphite is made out of. Graphite is really like a stack of graphene. Just like pages in a book, they easily come apart. And so easily that there's so little bonding between the different layers of the graphene in a stack of graphite that their properties are virtually identical. And that is almost obvious. I mean, there's no bonding between the layers, so how can one affect the other? And they don't. In fact, this might come as a surprise, but virtually all the physical properties and chemical properties on graphene and graphite are equivalent. There is a difference, and it's very subtle. It's actually graphene and graphite have a very different electronic properties, and it's so subtle that even if you have two graphene layers and you put them on a different orientation on top of each other, you change electronic properties. So it's a subtle difference. But for all the other properties that are non-electronic, actually graphene and thin graphite and graphene are virtually identical. And so Jim just gave a long talk on this, and he used mainly thin graphite, but it's called graphene now. That's just become the way to describe these things. So how old is graphene, and how old are graphene products? Actually, the so-called first product that I would say is real graphene was called Aquadag. That's on the right side. And that was invented in 1905. And 1905 is a long time ago. And I use it as in my school, during my graduate work and all that. And actually, it was invented by a guy called Atchison. And he was a guy who started Union Carbide. And he actually was the first one who made silicon carbide. And he knew how to make silicon carbide into graphene, and that's what he made this paint out of. That was in 1906, so it's really old. So what I'm interested in is on epitaxial graphene. So what's epitaxial graphene? Well, let me look at the word. Epitaxial graphene comes from epi, which means above, and taxis, which means in an ordered manner. So what that's all about is I was looking for making electronic material. So if you put the graphene on silicon carbide and it's ordered, it's epitaxial, then you know where every atom is. And if you want to have an electronic material, it's essential that you have this kind of graphene. If you don't know where the atoms are, you cannot nanopattern it. So this is really a critical thing. So that's why in the bottom you see there, epitaxial order is absolutely required for nanoelectronics. You cannot do it with just Scotch tape and putting it on something. You will not have material that you can pattern to make electronics. So I know I'm rushing a little bit. I don't know what the time is because I don't have a clock available. Okay. Oh, wow. Is that for real? Okay. They're very generous. Okay, that makes me relax a little bit, so that's good. I'm sorry about that. There was a little bit issue about how much time there would really be. So I have enough time to do this in a more gentle way. So how do we make it? Well, Jim just gave a very interesting exposition how he made his graphene out of basically anything. Well, we do something that is not as radical, but actually in many ways very similar. What we do is we take a piece of silicon carbide, which is a crystal. Let me go back one here. Hang on. Let me go back. I'm sorry. You see, I know how to do a whole bunch of things, but I do not know how to handle a clicker. Now I'm getting lost. Now I got really lost. I'm sorry about this.
One point of clarification, Walt, is that that's the entire session.
Oh, yeah.
We do have another speaker.
Yes, I know we
Why
do.
don't we get some AV support for his slide?
Yeah, okay. I'm sorry.
I
The
think you have
clicker
about-
is
Yeah,
the clicker is getting me confused.
I think you have about, what, 10, 15, 10 minutes.
All right.
Yeah.
That's
Sorry for the confusion.
yeah.
Try that.
Okay, which one's forward and which one's backward?
That's forward, the big button. Small one's backwards.
Okay.
Are you there now?
Well, let me see where I am. It's not in presentation mode. That's not good. Well, there should be a presentation mode for the PowerPoint.
And I don't know how to use it because I didn't set this up. I'm sorry.
Okay. This is getting difficult. There we go. So there's your silicon carbide crystal, and it's as flat as it can be, and the graphene goes on top. And so how do we make it? That's where I went. Okay, it's very easy. You take a piece of that silicon carbide and you simply put it in a quartz tube, and then which is then inside of a so-called graphite susceptor or a little graphite cylinder, and you heat it up to temperatures on the order of 1600 centigrade, and spontaneously you get this graphene layer that will grow on top of the silicon carbide. That's demonstrated over there. So there is your graphene sitting on top of the silicon carbide, and it can do it two different ways. You have two faces for the silicon carbide. You have a so-called silicon terminated face with the yellow atoms, and you have a carbon terminated face on the back. So if you grow it on the silicon terminated face, you get a graphene layer that's actually periodically bonded to the silicon. The graphene is bonded to the silicon on the surface, but periodically, if you grow the graphene on the other side, you'll actually have a freestanding graphene layer. So there's two different kinds of graphene you can make. One which is bonded to the silicon carbide, and actually this becomes semiconducting graphene. And the other one is quasi-freestanding. So that's very interesting, two different kinds of graphene. Now I'm going to talk a little bit about the silicon technology, because if we were trying to make a new electronic material, should be motivated a bit. You know that silicon electronics is based on silicon wafers, also single crystal. And, well, you use very expensive lithographers. The single crystal silicon is there. It's as big as a man, and wide is about a foot wide. And that's how you do it. And you know what happens next. You go through this patterning, and ultimately you make chips out of that through this lithography and all these processes. And ultimately you end up with these enormous data centers made out of these chips. That's what you do. So this is the Tesla's center called Cortex. And it's enormous, with enormous amounts of stuff in there. And why do you want to do all that? Well, you want to make well, you want the enormous AI requirements for computing is really getting really heavy right now. And as you might know, many years ago, Gordon Moore already said that this whole silicon technology will come to an end at some point, and for very obvious reasons. You can't make devices much smaller. Devices are power hungry and overheating. You can't make them much faster. So a new electronics material has to be developed in order to be able to continue growth in electronics, and also a new electronics paradigm. So those are the two things what you need to do. And so what do we have to play with? Well, silicon does a lot of things, but it does not support quantum coherent electronics, which is really, to me, the next step in electronics, or something called spin-based electronics, or spintronics. And we really want to introduce those aspects into electronics, and that was my plan, in fact. So now we can look at what nature does, by the way, and I think this is quite interesting. So I can compare, since I already compared Tesla things already just a second ago, you can compare Tesla's self-driving capabilities, and you know how that works. We have an enormous computer that actually makes the programs, and actually you have to teach it about self-driving, and that you can feed into your onboard computer. And that's all. If you want to have a self-driving Tesla, what you really hope to do, that it drives around hands-free so it won't bump into things. And but that's an enormous amount of technology and very heavy computers that need to all this to happen. And what do you want to end up doing all that? Why you want to do that? Well, you want to have a self-driving computer that does not crash into things. That's one thing. And it has to be able to detect where it is. So in nature, we have another thing that does it very well, and that's mosquitoes. And if you ever walk around, you will notice that mosquito does this very good. It sees, detects that there's a collision might happen. Here's this guy, and he's going to swat the mosquito. It sees it, and then it takes off just in time and does everything just right. And it does that with 200,000 neurons, 60 nerve centers, and 2 actually are used to find you, which is its food. So it does a lot. And let's look at what its weight is. The weight of his brain is 10 micrograms. It uses 1 microwatt, and its size is 2/1000 of an inch. And it actually does exactly what the Tesla computer does, if you think about it. So if you can wire the mosquito to your Tesla, you're doing really well. Or you can, and who knows, maybe I know that Musk is thinking about attaching wires to brains and all kinds of stuff. Maybe he can do it to mosquito and can save himself a lot of money. So that might be a way to go. But the fact is that the complexities of making neurons, we had talked about that yesterday a bit, is extremely complicated, and we just can't do it. But the point about all of this is we still have a factor of 100 million to gain. Moore's law has to go for maybe a few hundred years at the same rate to get that level of enhancement. So a factor of 100 million is still to be gained in electronics, if you look at it this way. Now, you might object with my analogy, but I think it's accurate. So let's look at that. Well, of course, we are not going to make a biomorphic, if you will, computer. So, but I do want to talk a little bit about, well, I'll do this. Yeah, how do we get there? Actually, like I already said, it was working on prior knowledge. So we knew that graphene grew on silicon carbide. We also knew that theoretically graphene nanostructures can be turned into semiconductors just by their shape. We also knew that there's a so-called edge state called zero energy state, and that's from prior work. And myself in the late 90s, I had worked on carbon nanotube quantum resistors, and there too we found out you can get fantastic performance out of carbon nanotubes. Now the carbon nanotube is a true precursor of graphene. It's also called a rolled graphene tube. And from that, well, very early on, I looked at, okay, now I'm getting really pushed. Yeah, I'll do my best. So you can turn the graphene into a semiconductor. This is what I said. Well, I'll have to race through this. So there is basically a proposal and that to the NSF about this in 2001, and then finally we submitted a patent for it as well. So why do we want to have 2D electronics? We do it for size scaling, for lower power, for making special kinds of transistors, to make interconnected device structures, and to reduce complexity and all of that. And in the case we really want to go to quantum computing, that is really where we're aiming for, to use something that is not used in electronics now. It's the quantum interference and quantum properties. That's what we want to introduce. So, and I'm going to race through this really quickly, and I can do that. So here we have We have already demonstrated with our new material that we can get scaling, high speeds, quantum coherent spintronics, and novel 2D materials, novel zero-energy topological edge state, and semiconducting graphene. I'm going to flash through the slides because they'll be quite meaningless for you. Because I'll have to spend so much time on it. So we already showed that you can take this epitaxial graphene and turn it into integrated circuits by just like with silicon technology. We already made the fastest transistor you can imagine with epitaxial graphene by patterning it. We were able to demonstrate so-called quantum coherence, and this is very good, which is a precursor to all of quantum computing, and we already demonstrated that. We were able to show spintronics, and actually, well, spintronics is also a novel way of dealing with electronics. We were also able to do that. This is something that's very interesting. We were able to put different materials under the graphene to make new kinds of 2D materials. Finally, this is something that's brand new. It's called ultra-high mobility semiconducting epitaxial graphene on silicon carbide. The one big deal about graphene is that it's a metal and not a semiconductor. So we were able to convert it into a semiconductor. Well, I already told you that some time ago in the very beginning, that we have a newest, now very recently made a semiconducting form of graphene. And this one proves to be the best two-dimensional semiconductor that we in existence. It has a band gap of 0.6 volts or so. It is 10 times mobilities that are much larger than that silicon. And this was really originally the holy grail. Since graphene is not a semiconductor, can you turn it into a semiconductor? And yes, we can. And it can be done on wafer scale. So we have a two-dimensional semiconductor right now made out of graphene. Nobody in the world has been able to make a two-dimensional semiconductor that you actually can pattern. They made two-dimensional semiconductors, but not one that you can actually turn into good electronics. And I actually already had patented this in 2012. I already knew that it was going to be a semiconductor. It just took a couple of years to make it all happen. And so this is a patent. In fact, all this stuff is patented, and it's all US patents, by the way. And here's another one for the semiconducting graphene transistor. Finally here, and I leave this to the last, but it's actually quite important. Now we have something that really came as a surprise. And there was a lot of discussion about things can surprise you when you're doing research. And this is one of them. We actually found an edge state that physicists still do not understand. It is a state that lives on the edge of the graphene, epitaxial graphene, that seems to be having absolutely no resistance. It goes over it's a one-dimensional state. It goes under the name of a topological zero energy state. That's the technical name for it. I've worked with quite a few theorists on it, and we made 2 papers on it. The first one was that we actually saw the effect. That's the bottom paper. And the other one, we proposed actually an entire electronics platform based on this edge state that happens in nanoscopic graphene devices. So this, I believe, is the most important discovery in graphene to date. And not semiconducting graphene, not graphene itself. This unusual state, this topological state, which is one-dimensional, goes all the way down to almost atomic sizes, widths. So this is really a big deal. And to put a little bit of physics behind it, Okay, now this is my last slide here. Okay, this really is. And it's a complicated one. It basically, okay, what it basically comes down to, that we believe that the zero energy state actually is happening because the electron is part electron, part hole, part anti-electron, going in the opposite direction. You say, how can it possibly be? Well, that actually can be because we have these 2 states are correlated. This is a quantum mechanical effect that things can actually know of their existence even though they're far apart. It is very unusual. It's absolutely, if it goes under the it resembles something called a Majorana fermion, which has been basically people have been looking for at least 100 years now. There's a big story behind that. Any case, I don't want to go into the details, but if this thing pans out, then we can have quantum coherence, basically resistanceless electronics at zero energy. So, of course, energy will be dissipated, but we're looking at an entirely different way of doing electronics. It has nothing to do with the standard silicon transistors anymore. It's really different. And okay, and then they're going to kill me. Okay, okay, you know what? I'll let you look at this. Maybe I'll leave it up for you, and this is what I'll have to do. Thank you. Sorry about that.
Good morning, everyone. It's a pleasure to be here at COSM. I'm from MTM Critical Metals. Dr. Tour already mentioned, but we're commercializing his flash Joule heating technology for metal extraction. And we're listed on the Australian Stock Exchange, but our primary operations are based in the US, in Texas. Just do a quick survey. Can I get a show of hands as how many people here drive an electric vehicle? And just another quick question. Who here would think, does an internal combustion engine car versus an electric vehicle, which contains more metal? Who would say less? Yeah, that's correct. It's on average about 6 times more metal is needed in an electric vehicle compared to a traditional combustion engine. The first topic I'd like to discuss here is how dependent the US currently is on foreign nations for their metal supply. Now, most of the technologies discussed here today and during the COSM conference are reliant on metals such as rare earth elements. There's about 17 rare earth elements on the periodic table, and all 17 of them are used in some shape or form in smartphones, electric vehicles, and artificial intelligence. Gallium is one in particular that's used ubiquitously in semiconductors. And as you can see from this list here, the US is 100% reliant on import from China for gallium, as an example. Almost the same story for rare earth elements. We're focused on trying to bring the supply back to the US using flash Joule heating technology. And as you can imagine, this is a significant strategic vulnerability for the US, having so much reliance on a competitor like China. The next topic I'd like to discuss is the current major disconnect between metals and the technologies that metals go into, such as artificial intelligence. Now, if you did a survey of the S&P 500 back in 1925, approximately 40% of the index was comprised of metals or energy-related stocks, so natural resource-based stocks. And that grew to almost 50% in the 1970s during the oil shock. And whereas last year, that has dropped to a dismal 5%. So this really says that the world is now more reliant on metals than ever, yet they're not really valued by investors because mining is a really tough business and it doesn't have the attractive gains that you might get with a traditional growth stock. But this trend seems to be changing. And gold is the first metal normally that signals such a change. And gold has been increasing in value over the last 12 months and pretty much outperforming most other assets. And we believe that we're on the cusp now of the next major commodity supercycle. So it might be time to rebalance some of your tech portfolio into more metals-based equities. Now back to the electric vehicle metal intensity. So a traditional Tesla contains about, in a typical battery, contains about 200 kilos of metals, such as lithium, nickel, copper, and cobalt. Now, to extract these amount of metals, would anyone have an idea of how much metal, how much of the earth you need to mine to get to make a traditional EV? It's about 1.5 million pounds of earth that you need to mine to produce a typical EV. So as you can imagine, that's a significant environmental footprint. Another major metal consumer is data centers, which have been mentioned several times at this conference. And this list here shows the metal intensity per megawatt of a typical data center. An example close to home is Microsoft's recent Chicago data center, which needed almost 2.2 thousand tons of copper, which is about 5 million pounds. Now, to mine that amount of copper, you need to move about, it's estimated about 1.7 billion pounds of earth needs to be mined. And data centers are more ubiquitous in the US than anywhere else, so it's more relevant here than anywhere else right now. Back to rare earth elements. So these are crucial for most military defense technologies. So in a typical F-35, there's almost half a ton of rare earth elements used. This goes up to over 2 tons for a destroyer and over 4 tons for a submarine. In an average smartphone as well, there's 16 of the 17 rare earth elements are used in some shape or form for a various technological function. And they're also used ubiquitously in electric vehicles and wind turbines. Another very prominent example is copper. So copper is probably the most dominant metal to achieve this net zero ambition that has been set. Now, to put into perspective, to achieve the target set to achieve net zero, we would have to mine 3 times more than the sum total of all the copper mined in human history. So copper is one of the oldest metals that's been mined, over 3,000 years. And to achieve net zero, so we need to mine 3 times that in the next 25 years. It doesn't really seem practical, does it? Because most of the grades of the ore bodies that are currently in use are all declining. All the easy stuff has been found. And because I mentioned the capital has been starved from most mining-related equities, money hasn't been put into finding new deposits. And copper, another copper example, where of the top producing copper mines in the world, over 20% of them were discovered over 100 years ago. So we're basically reliant on archaic mines. And these mines have to go deeper and deeper to get to the ore, which means you have to move more earth, bigger environmental footprint, etc. So where's all this metal going to come from? Now back to rare earth elements and how the US is really vulnerable at the moment. So China only contains about 30% of the world's rare earths in the ground, so 30% of the reserves, yet they control almost 100% of the downstream refining of rare earths. This includes separation, the metal production from rare earths, the alloying, and the all-important magnet production. So the neodymium iron boron magnet is the key technology that underpins electric vehicles and wind turbines. And China right now is this dominant supplier. And really this was all kicked off back in the 1980s by Deng Xiaoping. And the real shame here is that the technology used to both figure out how to separate the rare earths from one another was developed here in the US as part of the Manhattan Project when they were trying to purify uranium ore. So there's rare earth element contamination in the uranium ore that they had from the Congo. And the Ames lab, as part of the Manhattan Project, they figured out how to separate these rare earths. And the technology was further developed into a company called Magnequench, who invented the neodymium iron-boron magnet. And Deng Xiaoping acquired the rights to that technology in the 80s, and it personally enriched him and his family significantly. And ever since basically the 80s, there's been this technology transfer to China, who are willing to do the dirty job of processing rare earths. And they have now produced more engineers who specialize in rare earths than the sum total of engineers currently in the United States. So they are by far and away the world's leader on rare earth metallurgy and processing. And what has been the environmental cost of this? Most people here in the room has probably benefited from this. So if you've ever had a Nintendo, Game Boy, or a flat screen TV in the last 40 years, there's almost 100% probability that the rare earths within it came from one of two locations in China. This is the Baotao mine in Inner Mongolia. Has been the world's biggest supplier of rare earths for the last 40 years. And the BBC called this one of the biggest ecological disasters of all time. They basically pumped their radioactive tailings into an unlined dam. And this dam is so big it can be seen from space. Another major source of rare earths for the last 40 years has come from these clays in Myanmar and southern China. They're called ionic clays. And the method of extracting them is as basic as drilling a hole into the side of the mountain, flushing acid through it, and collecting the rare earths thereafter. Most people in the room have benefited from the rare earths from these deposits. That seems to be the end of the slides for some reason, but the primary message I was trying to make here is that all of the technologies that underpin all of our modern life, in the West, we're 100% reliant on China for that. And with a technology like flash Joule heating, we've got the opportunity now to more onshore metal supply back to the US. Because as one example Dr. Tour already gave, we can recover the metals from spent lithium-ion batteries, from printed circuit boards, which contain a significant amount of metal. And because of we don't need huge, massive blast furnaces to have an economically viable project, we can set up these locally near suppliers. We can set them up at recycling plants that already exist. And we're already in discussions with several major players who hopefully will one day have an offtake agreement with us in the near future. And we're also looking at improving the mineral processing industry, primarily in Australia, where our headquarters is. We've had a lot of success with lithium, as Dr. Tour already mentioned. But essentially, lithium is one of the most difficult metals to extract from its mineral ore. You need a huge amount of acid and energy to get it out. As Dr. Tour mentioned, we can potentially cut out 80% of the unit operations for a typical lithium refinery using flash Joule heating under a chlorine gas atmosphere. So it's really game-changing potential for both recycling and also mineral processing improvements. And that's essentially it. We're listed on the Australian Stock Exchange, and we will hopefully soon also have an OTC listing for US investors. Thank you.